Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving examples using indeterminate axial systems. This is part 3 in a multi-part series. In this video, we're continuing the example we started in the last video, which is evaluating the internal axial forces and drawing an axial force diagram for the segmented bar system shown, members connected end-to-end in series. In the first video, we set up the problem by identifying the equilibrium and compatibility equations needed to solve the problem. In this video, we'll solve the system of equations two different ways. The first method that we'll demonstrate is to actually set up a matrix system of equations. I believe this is also always your best bet, your most efficient and easiest method if you know how to do it. Here we've written the equilibrium and compatibility equations so that it's easy to define the matrix system of equations, and I'll go ahead and do that. This is we have three equations, three unknowns, F1, F2, F3. So we're going to set up a matrix, a 3 by 3 matrix, a vector of the unknowns, which are F1, F2, F3. Those are going to be equal to the values on the right-hand side. The first equation is 1 times F1 minus 1 times F2, and F3 is not in this equation, so we'll put a 0 here, plus 0 times F3, and that equals 68 kilonewtons on the right-hand side. The second equation doesn't have F1 in it, so we'll put a 0 there. It's negative 1 times F2 plus 1 times F3 equals 125 kilonewtons. The third equation, the compatibility equation, is F1 times L1 over A1 plus F2 times L2 over A2, F3 times L3 over A3. So those are the coefficients that go in that third equation. It's equal to 0. Let's go ahead and substitute the values in for L1, L2, L3, etc. So I'll rewrite the system over here as shown. 1, negative 1, 0, 0, negative 1, 1. And then I'll just go ahead and substitute the values for L1, A1, etc. and convert them to millimeters. So one thing I want you to recognize here is because the right-hand side is 0, the units are going to cancel out because they're the same for every term. So we really don't have to worry about using like units. But in order to avoid confusion, we'll go ahead and do that. We'll list every quantity in millimeters. So L1, 4,000 millimeters, divided by A1 is 500 millimeters squared. L2, 3,000. A2 is 800. L3 is 4,000. A3 is 800. And all those terms are per millimeter, but again, that's going to cancel out. So that's why I'm not specifically listing them. Okay? This multiplies the vector F1, F2, F3, and equal to the right-hand side, 68, 125, and 0, all in kilonewtons. Okay? Now, the way to proceed with this, I'll just simply say solve. Use your calculator. If you have an equation solver on your calculator, use MATLAB, use MathCAD, or any numerical solver of your choice. My favorite is MATLAB. Very simple and easy to enter the matrix system of equations in there. At any rate, you either know how to do this or you don't. If you do, take advantage. It's very quick and easy. The result you should get, F1 equals negative 1.8 kilonewtons. That tells you it's compressive. F2 equals negative 69.8 kilonewtons. That tells you it's also compression. F3 equals 55.2 kilonewtons. That tells you it's tension. Circle my answers. Okay, so what if you're not so comfortable using an equation solver to solve the system of equations? You can proceed instead by manipulating the equations and trying to isolate variables, substitution, etc. This generally works well if you know how to proceed. Sometimes it can get very messy, and the way you approach it will determine whether you get caught in a big mathematical mess or if it goes fairly smoothly. In this problem, you see we started out and we did this in the first video, by setting up our equilibrium equations, substituting, solving for F1 in terms of F2 and F3 in terms of F2. So our approach will be to substitute for F1 and F3 into the compatibility equation and solve the compatibility equation. This is not the only approach that will work, but it's the approach that we've chosen to try to simplify the math. Okay, so we'll start out F1. I'm going to substitute the numbers in here. L1 over A1. We did this for the other method as well, so without too much description, I'll just go ahead. F2 times, was it 3,000 over 800 plus F3 times 4,000 over 800 equals 0. Again, those units don't matter too much. They're going to cancel out. Now we'll proceed to substitute in for F1 and F3 and manipulate a little further. So we have F2 plus 68 kilonewtons times 4,000 over 500 is 8, plus F2, this reduces to 3.75, plus F3 times 4,000 over 800, which reduces to 5. I'm sorry, I should be substituting in for F2 plus 125 kilonewtons for F3 times 5 equals 0. Okay, now let's gather all the like terms that multiply F2. We have F2 times 8 plus 3.75 plus 5, plus we have a 68 times 8, and we have a 125 times 5, and those units are in kilonewtons. Now we can solve for F2. Bring this term to the right-hand side and negate it. We get a negative 68 times 8 is 544, plus 125 times 5 is 625. That's in kilonewtons, divided by 8 plus 3.75 plus 5 is 16.75, and that reduces to negative 69.8 kilonewtons. Okay, just like before, F1 is going to be negative 69.8 plus 68, which is negative 1.8 kilonewtons. F3 is going to be negative 69.8 plus 125, which is 55.2 kilonewtons. We got the same thing we did using the other method. Okay? Your choice, you can approach it either way. Finally, the last part of the problem, we're asked to draw the axial force diagram. I wrote the forces down. This makes it really easy because the internal forces in each segment are the forces we want for the axial force diagram. Don't forget to label it force, axial force diagram, something like that, and indicate units. Okay, F1, negative 1.8 kilonewtons, compressive, so it jumps down by 1.8. F2, negative 69.8. I'm going to go down to 69.8. Remember, the difference is 68. This value here, 1.8. This one's 69.8. And the last one is 55.2. So I'm going to go up 55.2. This is positive, this is negative, this is negative. Okay, that's the axial force diagram. And the jumps look correct. And that could be one sanity check that you could do, is check that the jumps are correct. Another sanity check that we can do is look at the relative values in the segments, the forces in the segments. So notice that we get a large negative value in segment 2, and both of our external loads are pushing towards segment 2. So it makes sense that you would have large compression in segment 2. It makes sense that you have 125 kilonewtons pulling away, so it makes sense that you're going to have large tension in segment 3. So just by a little bit of inspection, I think the answers make sense. Okay, that concludes this example.